Dear all the friends, welcome to the 15th Energy Visions Seminar. I'm the host and my name is Ning Xu. It's a great honor to invite Dr. Jann Weinand to give a report. And the title is Exploring the Trilemma of Cost Efficiency, Landscape Impact, and Regional Equality in Onshore Wind Expansion Planning. The entire seminar lasts about an hour, of which the first 45 minutes are used for report and the remaining 15 minutes are used for discussions. Let me give an introduction to the speaker. Dr. Jann Weinand is head of the research group, Complex Energy System Models and Data Structures at the Institute of Energy and Climate Research, Techno-economic Systems Analysis at the Research Facility Jülich, Germany. His research focuses on the techno-economic and socially acceptable system integration of renewable energies in municipal and international energy systems. He holds a PhD in energy economics from the Karlsruhe Institute of Technology and a Master of Science in Industrial Engineering with specialization in mechanical engineering from Aachen University. Let's welcome Dr. Jann Weinand to begin his report.
Yeah, thank you very much for the introduction. So let me share my screen. And thank you also for this kind invitation and the opportunity to present my previous work here in the seminar. So this presentation will mostly be about onshore wind siting, and the historic onshore wind siting and how the future expansion could look like, and is mainly based on two publications you can see below on the slide, one in Advances in Applied Energy and the other one in Environmental Research Letters. So at the beginning, I would like to motivate this topic. Why is onshore wind siting even important, and which criteria have to be used in onshore wind siting, and how could they be used? Then I will show you some results on the historic onshore wind turbine siting, and give you also some scenario results on how the future turbine siting could look like. And I will conclude this presentation with a discussion. So onshore wind energy is a low-cost electricity source and therefore has become a mainstream electricity source worldwide, and further cost reductions are expected by 2050. So also in Europe, it's a leading renewable energy source by installed capacity, and it is expected that this capacity will significantly increase by 2050 to achieve the climate targets. However, the deployment of onshore wind has stalled in many European countries, and especially because of growing social disputes around this technology. And in this diagram here, you can see the example of Germany, where you see the newly added onshore wind capacity per year. And as you can see, after record years in 2014 and 17, the added capacity has sharply decreased in the last years. So for us, it was important to understand which were the criteria which were of the highest importance in the historic onshore wind siting, and how could these criteria be incorporated in future onshore wind expansion scenarios to help accelerating the expansion again. So in previous research, a group of experts has identified 4 key factors for onshore wind deployment. The first one is socially mediated health concerns, for example, through negative externalities like noise, or there are also decreases in property prices. So there are some burdens which need to be distributed among inhabitants, and this could either be, for example, be measured by the affected population, on the one hand disamenities, or on the other hand the turbines could be more evenly distributed, which would mean more to increase the regional equality of the distribution. On the opposite, there are also financial benefits which could be distributed, like job creation or economic benefits in the region. And these financial benefits could be measured by costs or also regional equality. Then the third factor is meaningful engagement, because the plannings in the past have shown that projects are increasingly opposed if the local stakeholders are not involved in the planning process. But this is really challenging to quantify, and yeah, for us it wasn't possible to incorporate this, but maybe future research will find a way to do that. And the fourth factor is the treatment of landscape concerns and the landscape impact. So the visual impact on landscapes is one of the main reasons for opposition against onshore wind in Europe. And especially in landscape with a high aesthetic quality or scenicness, wind turbines are increasingly opposed. And this could therefore be measured by landscape quality ratings. To give you more details on how these different criteria could be measured, first of all, cost effectiveness could be measured by turbine LCOEs. LCOE means levelized cost of electricity, and it sets into relation the cost of a turbine with the electricity generation of this turbine. So if we have a very windy site with a high electricity production, then the LCOEs will be lower. So the turbine will be very cost effective. The second criteria, disamenity, is usually restricted to an area of about 4 kilometers. You can see here in the diagram the monthly disamenity costs, which decrease to 0 at a distance of 4 kilometers. And this could be measured by creating these geodesic buffers around turbines that you can see here, and then intersect the population numbers with these buffers. And these are usually available on grid level. For example, in Europe, these are available on a 1 kilometer square grid. The regional equality can be measured by the Gini index. This is an index named after the researcher Gini, and it gives an indicator of how even a distribution is. So in this case, we want to distribute the turbines as even as possible, and use as a criterion for this, use the annual generation of wind turbines. Has a higher electricity demand, more wind turbines would have to be installed in this region. And this could be measured at different spatial scales, for example, the county level or the municipal level. But in the following slides, so in our study, we use the NUTS 3 level. So our results I will show in this presentation are based on a Gini index on the NUTS 3 level. And the landscape impact, I already said that this was very important in the past, and the more scenic a landscape is, the higher is the chance that a project is rejected. But how could we measure these scenicness ratings for a whole country? There were two approaches or two studies which achieved this to get scenicness ratings for an entire country. The first one, country, and then these photographs, or the scenicness of the landscapes in the photographs, was rated by a representative amount of inhabitants. You can see a voting board here on the right side, which they used on their website. This was the scenic or not game, where a landscape was shown, and then the participants could indicate the scenicness, with 1 being not scenic and 10 being very scenic. In another approach, landscapes photographs weren't taken for every area of a country, but only for a few reference spaces. And in this case, these areas should be as representative as possible of the whole country. And the photographs should also be connected with metadata like land use type, infrastructure, or elevation. Then, as in the first approach, scenicness ratings are needed for the landscape photographs. And in the third step, regression analysis would be conducted by using the metadata and thereby extrapolating the scenicness ratings to the whole country. To show you the results of these two approaches, the first one was used for Great Britain, which can be seen here. There are 217,000 photographs were taken, which covered 95% of all 1 kilometer squares of Great Britain, and these were rated by 1.5 million ratings. On the bottom here, you can see the histogram of the scenicness ratings, where you see the scenicness intervals here from 1 to 10, with 1 being low scenicness and 10 being high scenicness, and the mean scenicness in Great Britain is 4.4 according to this data set. And the colors here refer to the scenicness levels. So as you can see, especially Scotland is rated as very scenic, or parts of Wales as well. Then the second approach was used for Germany. There, the authors took photographs in 30 reference spaces with an area of about 130 kilometers square. And these photographs were then rated with about 45,000 ratings. And the regression resulted in scenicness ratings for every square kilometer in Germany. As you can see in Germany, especially the middle of Germany and also the southern Germany is rated as very scenic. For example, here the Black Forest, the Bavarian Forest, or the Alps. And what you will probably hardly see in this figure is that the coast here in the north of Germany is also rated very scenic, but in general the north isn't rated as scenic as the south. If we now want to investigate the future expansion and also the existing turbine stocks, we first of all need data for this. And for the potential turbines, so the turbines which could be placed in the future, we use a data set from our institute on technically feasible turbines in 2050, where we incorporated all needed technical aspects like minimum distance restrictions, for example, to settlements or protected areas, and also future turbine designs and investments. This resulted for Europe in about 3.3 million turbines, which you can see on the map here as red dots. And this allows for a spatially explicit turbine placement. Among these locations, about 110,000 turbines or locations are already occupied with existing turbines, which you can see in this figure here, also displayed by red dots. And the mean LCOEs at these locations by 2050 would be 5 eurocent per kilowatt hour. And the mean affected population in a radius of 4 kilometers around turbines is about 4,000 inhabitants. On the right side here, you can see the Gini index, so how even the turbines are distributed in every country. And you can see that in many countries, for example, Romania, where the turbines are especially in the east of the country, or Germany, where they are located in the north, these countries have very high Gini indexes, and the higher the Gini index, the lower the regional equality is. On the opposite, Ireland, for example, has a low Gini index, so a high regional equality. The turbines are distributed very even. Here I show which potential is already exploited in Germany, in Europe, and in which countries for different LCOE levels. So the LCOE levels are here on the y-axis for 2050 and shown for the different countries in Europe. The bubble sizes indicate the capacity. So the blue bubbles show the potential capacity, which could be installed, and the red bubbles show the share which is already exploited. And the numbers you can see indicate the exploited share if it's above 5% for this scenicness range. And in Europe, so far, only 2% of the whole potential is exploited. And as you can see, we have higher exploitation shares for lower scenicness levels. So if for lower LCOE levels, sorry. So if the LCOEs increase, then the exploitation shares decrease. And there are some countries like Germany here and Denmark for every LCOE level, despite having very low and not so cost-effective potential. On the other hand, we have some countries like Finland, Ireland, Norway, or Sweden, which have a very large and cost-effective potential, but there the exploitation shares are still very low. And to give you some more details on which criteria were important in the past, in the historic siting, in this diagram, we show the ratio of LCOEs on the y-axis and the ratio of affected population on the x-axis. For you, to remind you, affected population was to measure the disamenities. And first of all, it's important to understand this diagram. So the ratio of LCOEs means that we, first of all, for every country, we had the mean LCOEs of the existing turbines, and then divided the mean LCOEs of the existing turbines by the mean LCOEs of all potentially possible turbines. So this means if the ratio of LCOEs is below 1, then the planners have taken LCOEs especially into account because they are lower than they would be on average for the whole country. And as you can see, the LCOE ratios for every, what I forget, the bubble size indicates the capacity that is already installed in the countries. And as you can see, most of the bubbles, so for every country, the LCOE ratio is below 1, which again shows that LCOEs were of high importance in plannings in the past. But this is not true for disamenities. As you can see, many countries are above the threshold here. And no country is located in this third quadrant where the ratios of both criteria would be above 1, and this is probably because the projects which would be planned here would have been rejected. There are also some countries like Greece here or Spain which show good practice because the LCOEs and also disamenities could be considered. But on the other hand, there are also countries, I think Sweden is a very interesting example. Here the LCOEs were considered, but the affected population by the turbines seems to be of lower importance. And here the ratio is quite high. But also for Sweden, we see that projects are increasingly planned in the remote and sparsely populated north. Like the Ösnosberget wind farm project, which will be the largest single onshore wind farm when it's completed with about 750 megawatt. Here I give you more details for Germany now. As I told you before, most turbines are installed in the northern federal states, which have low scenicness values and very good wind resources. Here you can see the turbines per 1,000 kilometers square for the different federal states in Germany, and ordered by decreasing order. And you can see the federal states with the lowest turbine numbers are Bavaria and Baden-Württemberg, which are in the south of Germany. And as I have shown you before on the scenicness map, the scenicness in the southern federal states is especially high. You can see this also in this diagram that the scenicness ratings tend to increase for federal states with lower turbine numbers. We also learned that the regional equality in Germany is very low so far, with about 25%, and therefore there was a policy target introduced in Germany, the South quota, which demands a share of turbines in the south. So the line is somewhere here, and then turbines below here should have a share of about 20% in the future, but currently it's only about 10%. The potential in Germany is 160,000 turbines, and which would mean about 620 gigawatt and an energy yield of 1,300 terawatt hours. You can see this here in the diagram, depending on the LCOEs over the cumulative onshore wind potential, and then for every scenicness level. And as you can see in Germany, the largest and most cost-effective potentials are for scenicness levels 4, 5, and 6. And in this diagram, you can again see the exploitation shares, this time only for Germany, and for scenicness ratings from 1 to 9, with 1 being low scenicness and 9 high scenicness, and here for different LCOEs. And again, you can see the exploitation shares decrease with increasing LCOEs, and they also tend to decrease with increasing scenicness. So both of these criteria were probably of high importance for the historic siting in Germany. But how could we now that we learned which criteria are important, how could we plan the future expansion? In our studies, we decided to use an optimization approach, where we gave as input the potential turbines, and then for every turbine, a binary variable could decide if this turbine should be installed. Then we also have for every turbine the cost, the scenicness, or the affected population. And you can see that every criterion is multiplied with a weighting factor. And in this case, the weighting is either 1 or 0. And in the following, I will only present results where we have only one weighting as 1 and the others as 0. So we do not show a multi-criteria approach, because it's very hard to decide how or how high which weighting should be in relation to the other criteria. And then in the optimization, the specific capacity target has to be achieved. In the results for Germany, I will show it's 50 gigawatts by 2050. And so many turbines have to be installed until this capacity objective is achieved. Then there were also some equations introduced to limit objective values to be able to calculate Pareto curves. In this case, the costs of all turbines are restricted by a maximum allowed cost limit. And in this case, for example, we could minimize the scenicness of all turbines, but also restrict the costs by a certain limit, so that the costs aren't too high. For Germany, I show you now 4 different scenarios. First of all, the existing turbines, which you can see here again, are associated with LCOEs by 2050 of 6.5 eurocent per kilowatt hour. 1.4 thousand inhabitants are affected in a 2-kilometer radius on average. The mean scenicness is 4.5, and the mean regional equality in Germany measured on NUTS3 levels 25%. If we now minimize the LCOEs of the turbine locations, then as you can see, most turbines are installed in the north of Germany and also a few in the south of Germany. This is because in the north of Germany, there are very good wind resources and therefore very low LCOEs. On average, what is true for every scenario that I show now, for every expansion scenarios, that most of the criteria are below or are improved in comparison to the existing turbines. For example, for the minimum LCOE scenario, the LCOEs are about 30% lower than the effective population numbers, and the scenicness is about 5% lower than for the existing turbines. If we minimize the scenicness of the turbine locations, then we again see that most turbines are installed in the north, also some in the middle of Germany, but in general, the locations are the same as minimum LCOE scenario, so we have many no-regret locations in this case. So the trade-off between cost and scenicness is weaker in Germany. If we try to minimize the effective population to 200 inhabitants per turbine, this would imply 60% higher turbine LCOEs, and the turbines would be mostly placed in the northeast of Germany. And then there's also a scenario where we maximize the equality, which could be maximized to about 40%. But in this case, all other criteria would be worsened. And so a certain amount of regional equality is needed to achieve the policy target of the South quota, but the stakeholders probably shouldn't consider one of these extreme scenarios, but one which takes more than one of the criteria in account simultaneously. And I also said that with our approach, we were able to calculate some Pareto curves. I already said that the trade-off between mean scenicness and mean LCOEs, which I show here, is quite weak. But what we can also learn from this curve is this curve was created by decreasing the mean scenicness every time by 10%, and then minimizing the LCOEs. And what we can see is that decreasing the scenicness by the last 10% leads to the highest cost increase. So if a stakeholder would like to involve both criteria in the planning, then the optimal scenario would lie somewhere on this curve, depending on his plan. And so in this case, this is without considering regional equality. If we now say we also want to simultaneously consider regional equality, then we can see that this curve moves right, and to the top, so the scenicness and the LCOEs increase, but also this curve is much smaller. So if we simultaneously consider equality, then this restricts our planning flexibility significantly. And the results I showed for Germany, it's important to understand that these are not really generalizable. Because, for example, the weak trade-off I showed for scenicness and LCOEs, this is also not transferable to all regions in Germany. For example, if we take other system boundaries, like smaller regions like Bavaria, then we see that there the trade-off is much higher than for the whole country. And this is also true for Great Britain. We see this in this figure where we show the LCOEs over the scenicness values and the potentials. And in this case, the LCOEs for Great Britain are based on a study for 2020, whereas the LCOEs for Germany are for 2050. But what we can see is that the LCOEs decrease in Great Britain with increasing scenicness. So the highest, the low LCOEs are in areas in the north of Scotland, as I showed, where very good wind condition exists, and therefore the LCOEs are quite low. But in Germany, we do not really see a trend depending on the scenicness. So those LCOEs are at low scenicness levels. Yeah, to conclude this presentation, I would like to discuss the findings a bit. So we learned that there are 4 key factors for onshore wind deployment, like socially mediated health concerns, which we try to reflect with incorporating these amenities. Then the distribution of the benefits was considered by taking into account cost effectiveness and regional equality. But for the meaningful engagement, we didn't find a way to incorporate this yet. This should be investigated maybe in smaller case studies in the future, or maybe some researchers will find a way to incorporate this also in large-scale studies. Then landscape concerns should be treated seriously, which has been done in some national analyses, but at least to our knowledge, the data for scenicness ratings is only available for Great Britain and Germany. So we need more further data for more countries to repeat our analyses to learn more about the landscape impacts. I showed that there are strong disparities among countries in the historical onshore wind deployment. There were, for example, very low exploitation shares despite very high effective potential in Ireland and Sweden. The opposite was true for Germany and Denmark. And the historical siting showed trade-offs between the criteria like LCOEs and disamenities. For example, Sweden was an interesting case with very high disamenities and low LCOEs. And in general, LCOEs, disamenities, and scenicness were very important siting criteria in the past. On the other hand, regional equality has been largely neglected in the past. But for this criterion, we also have to mention or to highlight that the determination of regional equality could be done differently, or also has some weaknesses. For example, we compare the regional equality for different countries, but the NUTS-3 regions we use to measure these are quite heterogeneous. For example, in Sweden, the NUTS-3 regions are very large, and there are only a few. And in Germany, we have many NUTS-3 regions which are quite small in comparison. Then the spatial scale could have a large the regional equality is 25% if we measure it on NUTS-3 levels. If we go a level down to municipal level, then the regional equality would decrease even more. And this is because many municipalities lack onshore wind potential at all. We could also use other criteria for measuring regional equality, like land use per total area or employment. To remind you, we used the electricity generation by turbines, and then in relation to the electricity demand of a region. In the future expansion scenarios, there were also strong trade-offs involved. We could show that significantly better locations could be achieved than in the past, but it's also questionable if these expansion scenarios are feasible. And as I already mentioned, we need some criteria weighting. Unfortunately, previous research has shown that it's very hard for experts to decide which criterion should get which weighting. So there's more research needed. We also only incorporated the turbine LCOEs of turbines and didn't consider the grid integration costs, therefore neglected the overall system LCOEs of turbines. We could also in the future incorporate more renewables than only onshore wind. So for example, in Germany, a scenario with PV modules in the south and wind turbines in the north could be beneficial. And in general, these spatially explicit turbine locations should also be incorporated in energy system models, in holistic ones, to provide further insights. I think what also has to be highlighted is that the wind expansion targets probably cannot be achieved by siting decisions alone. So there's also policy action needed to introduce more procedural and financial participation of the inhabitants in wind turbine projects. Yeah, so that's it for now. I would like to thank you very much for your attention, and I'm looking forward to your questions. Thank you.
Thank you, Dr. Jann Weinand. It's a wonderful report, and the analysis is very comprehensive and in-depth. Next is discussion time. Does anybody have questions? No. Does anybody have questions? Yeah.
I think in the chat, someone.
There is a question in the chat room.
By Clemens Lohr.
Hello, can you hear me?
Yes, hello.
Okay. Thank you very much for the very interesting presentation. I have two questions. One kind of more related to your work, and then one that is a little bit beyond that. I would like to know, you've talked about the scenicness and about average values for German regions. How does potential or if you, for example, exclude areas with a scenicness of 6 or 7, would it mean that whole regions would be completely excluded, or is like there's a higher granularity, for example, in the south that would still allow like a more equal distribution?
Yeah. What I wanted to show is the map again. One moment. You should see it now. Yeah, so I think there is a granularity. So we have this for 1 kilometer squares, but as you can see, there are also some areas like here, the Black Forest, where we have high scenicness values for a very large region. So if we would exclude these high scenicness values, then yeah, much potential would be excluded in the south here. So for whole regions, and in this case, we would also restrict the values we could achieve for regional equality. Yes.
Mm-hmm. Okay, so there's an overlap of scenicness and also the actual potential that where you could install turbines.
Yeah,
okay.
Definitely. Yeah.
Okay. Yeah, thank you. Add a second question if none other is here to ask, I would just continue. So there have been, at least for Germany, I know there like politically discussed a lot of suggestions how to distribute the wind energy per state, for example. I would like to know, like, what do you think, in this suggestions, what criteria are actually being used? So because I mean you've talked about it and you've also expanded or added some ideas how it could be, but like what do you see actually being discussed?
Yeah, okay, yeah, that's a good question. I think if we want to achieve that every federal state has a certain amount of wind turbines, then I think one of the most criteria is the regional equality. And therefore, I think for every federal state to define a certain capacity or even better generation target, I think would be quite good. And then as I said, if we take, for example, Bavaria, there we still have all the trade-offs I talked about. So they also could decide among the locations there that they decide for example, for the highest HUEs and neglect scenicness maybe more. But I'm not sure which criteria are of more importance in this discussion. I think it's quite hard to say that.
Yeah, thank you very much. That was enlightening.
Thank you. Does anybody else have questions?
Okay, I have a question. Oh, hello?
Oh, please,
Can you hear me?
please. Oh,
Okay.
yes,
yes. Yeah, I'd like to know how you two decide the weight of the cost and the social responsibility. As you said that this study is aiming on how to decide the site selection of in the perspective of non-technical, but in the reality, that stakeholders always care about how the cost, but the public always care more about the landscape impact.
Yeah, that's also a good question. I think we didn't really incorporate this. We just showed the different scenarios, what it would mean to only concentrate on one of the criteria and what the trade-offs between these would be. And I think it's exactly what you said, that there will be trade-offs also for different persons. So if the inhabitants would plan it, maybe it would go more into the direction to reflect the landscape impact. Yeah, I think the stakeholders should try to use our results to think about how they could install the turbines, because if they only think about costs, this would probably lead to still having only less potential installed than, or turbines installed than we would like to install every year, and then we would fail to achieve our climate targets. So some trade-offs need to be considered.
Okay, thanks for that. But I have one more little question. That is the weight of the cost in this study is bigger than the other than the social responsibility.
Sorry, I didn't get the question.
As you said that the three criteria has weight, different weight. But I want to know is the weight of cost is bigger, or the other factors is more important in this study?
Okay, no, yeah, okay. We in this study we didn't use different weightings, so these were all equally important. And yeah, I think previous research has also shown there were some experiments with some stakeholders about which criteria should get which weighting in the future. So which one would be considered more important than others, and to set them in relation. The study showed that it's simply not really possible. So, and therefore we decided to not give the criteria some weights, but to show, kind of extreme scenarios where we just say, okay, if we concentrate on LCOEs, how would the turbine distribution look like? If we concentrate on regional equality, how would it look like? And then the stakeholders still could find some mixed scenarios where they say, okay, this could be the one. And I mean, for the Pareto curves we showed there, this is something which goes in this direction, where somewhere in the middle of the Pareto curve would be a scenario where the weightings would be differently.
Okay, I got it. Thanks.
Thank you.
Thank you. Any questions? Any other questions? Now, if anyone has questions, you can read the article later and discuss with Doctor. That's all for this seminar. Yeah, thank you, Dr. Yang, for your wonderful report, and thanks to every participant for the discussion.
Yeah, thank you very much again for inviting me. And
Thank
yeah,
you.
as you said to everyone, please feel free to write me emails, and maybe you have some further research ideas where we could collaborate. Yeah, thank you very much.
Okay, thank you. Goodbye.
Goodbye.